If you recall, yesterday we took a look at the dot product and how it relates to the line integral. Our line integral calculations involve the f dot dr at all points along a curve C. And what we saw in the calculation, when we think of f dot dr, we get the magnitude of f, the magnitude of dr times the cosine of theta, cosine of the angle between them. And so the way we could read this is how much of the vector field f is going in the direction of dr, the direction of the curve. How much of the vector field is going in the direction of the curve? Is the vector field adding to the direction of the curve? Or is there no effect because they're perpendicular? Or is the vector field going in the opposite direction of the curve? So dr is the direction of the curve. Should make a note of that. So the dr is the direction of the curve. Now this is all for line integrals. So f dot dr showed up in a line integral. At all the points on the curve C, calculate f dot dr. That's just what an integral is telling us to do. Calculate f dot dr at all the points on the curve C. Now we're starting to talk about what this could be used to represent. We started with work is equal to force times distance. That was nice and convenient because work is force as long as everything is going in the same direction. What was all that about? Okay. As long as everything is going in the same direction, we just multiply the force by the distance. But since force can go and direction don't have to go in the same direction, we can use a dot product. The reason that the dot product works is that the dot product is the product of the magnitudes times the cosine of the angle between the vectors. So that cosine of theta tells us how much of the vector field f is contributing to or subtracting from the direction of the curve. Questions? And then we broke it down into a bunch of cases. If the angle between the vector field and the curve is between 0 and 90, the vector field and the curve are adding together. They're both going the same way. We can say that the vector field is pushing whatever is going along the curve. If the vector field is perpendicular to the curve, then as we try to walk on the path, the vector field isn't doing anything for us. It's not hurting or helping us move along the path. If the vector field, if the angle theta is greater than 90, less than 180, that means the vector field is going in the opposite direction of the curve. So we're trying to walk along the curve, and the vector field is pushing against us. Starting from minimally pushing against us when theta is greater than 90 to going exactly in the opposite direction when theta is equal to 180. So imagine yourself walking along the curve. Imagine yourself walking along the curve and think of the vector field as the wind pushing against you. This will give us a sense of line integrals being positive and line integrals being negative. We calculate a line integral and we have a net positive. That means overall, the vector field was pushing things along that curve. The line integral is negative, then overall, the vector field is working against motion along the curve. Any questions? How's everybody okay? Everybody looks shocked. But you also look stunned. But you also look calm because I can't tell because most of it's like on fire. I used to joke that so you might think people are awake because you can see eyeballs, but I used to joke that one of the important college skills to develop is the ability to sleep with your eyes open. And I've been making this comment for years and years and years. And then what happens? Ryan Reynolds steals that shit right from me and puts it in his most recent movie. Now, the fact that he did it better than I would because he's funnier than I am, that's the important part, right? If you copy something and then do it better, I think the originator's got to be like, oh, well, you know, there you go. Plus, I kind of highly doubt that Ryan Reynolds has been secretly spying on me while I do math classes. I would be extraordinarily shocked to find out that Ryan Reynolds has installed hidden cameras to watch some yucks teach calculus. But there it is. What are we talking about? Oh, yes. So we thought this is what we were thinking about when we think about the dot product. We're thinking about the vector field being the wind and the curve being a path through the wind. Let's upgrade this. So when we talked about the fundamental theorems of calculus, we introduced a new kind of integral. We had no idea what it meant. We just wrote down some symbols. We talked about curl and divergence of a vector field. But I want to start by focusing on the integral part, just like with line integrals. Rather than worry about what this represents or what what applications this particular calculation has, let's at least get used to what the calculation is telling us based on what we know about the dot product and based on what we know about integration. In math class, we got to learn about what integration represents, and we got to learn about what dot product represents. So let's talk about flux integrals or surface integrals. So our flux integrals or surface integrals is just one dimension up from a line integral. We're going to calculate f dot dA, which is some small area. A dA is some small piece of the surface S. So we're going to make this calculation of f dot dA at all the points on the surface S. S is some surface. So S is some two-dimensional surface. So at all the points on this surface, we're going to calculate f dot dA. The integral tells us where we're going to be making the following calculation. And in this case, that calculation is f dot dA. It's another dot product. We got to think about what this dA might represent. So the dA is going to be a small piece of the surface. So dA is going to be some small piece of the surface, but it's a vector. It's involved in a dot product. I wrote an arrow over the A part. It's a vector. So it's not just the area of the surface. There's some vector attached to it. And we're calculating the dot product of the vector field at that point and this vector that's representing a small piece of the surface. This is just based on what we know about integrals and how they work. our vector field is possibly continuously variable all over the surface. So we chop the surface up into a bunch of little pieces and say that the vector field is constant on these little pieces. That way we can make our dot product calculation, and then we just add that to the next one. We just take the surface and we break it up into a bunch of bits. So S is this surface. dA is a small piece of this surface. Over which we assume that the vector field is constant. This is how we do continuous addition. This is the same thinking that we applied way back in Calc 2 when we first started calculating areas. We wanted to use length times width, but the stupid length was all variable. So we assumed that the length was constant over some small change in the width called delta x. Then we are allowed to multiply. Same thing here. Vector fields, stupid vector fields, all continuously variable. So we lock that down for some small region, dA, on this surface S. We make F constant so we can calculate our dot product. Then we add that up over all the points on the surface. But we still have this issue. dA is not just some area. It has some area, but it's not just some area. The magnitude of dA is going to be the area of that little piece. So the magnitude of dA is the area. But this dA with the arrow is a vector, so we got to think about what its direction is. So the magnitude of dA is going to be the area. We've got to assign a direction to this some small piece on the surface. It's got to be one vector so that we can make our dot product. Any suggestions for what we should use? Got a surface. I need one direction. We really only have one choice. There's a surface, we need to assign a vector. We will assign the normal vector. So the magnitude of dA is just the area, and we're going to give it a direction that's normal to the surface. So the magnitude and we'll take it the direction normal to the surface. A little bit different than our line integral. In our line integral, we took as the direction on the curve tangent to the curve. But We've got a plane that's tangent to the curve, and I want one vector, so we describe it normal to the surface. Any questions? So we're going to be doing a slightly different, some slightly different thinking about our surface integrals, our flux integrals. Line integrals, our favorite example is work is equal to force dot distance. So we can think of the vector field as either helping or hurting us as we travel along the path. Let's draw a picture of what's going on here. We're still calculating a dot product, so I've got some vector f from the vector field. And I've got some vector dA, which is going to be normal to the surface. So the way I've drawn it here, the dA, the little piece of the surface, we're drawing this dA perpendicular to the surface. And this is some piece of the surface that we're assuming is flat. And we're also assuming that the vector field is constant for that small square. So this is a side view of F flowing through the surface. That's going to be the thinking for our flux integral. We're integrating over S, F dot dA. dA is going to be normal to the surface. The vector field, we're going to imagine F flowing through the surface. Our dot product is still going to tell us about the part of F our dot product is still going to involve the magnitude of F times the cosine of theta. And this will just be multiplied by the area. And we can think of the vector field as stuff flowing through some surface. So when we calculate F dot dA, we'll have the magnitude of F times the magnitude of dA times the cosine of theta. So we're really doing a very similar thing. We're seeing how much of the vector field is flowing through, how much of the vector field is flowing through the surface. We're measuring the amount perpendicular to the surface. Line integrals, think about work is equal to force times distance. Flux integrals, or surface integrals, we're going to think of as flow through a surface. Everybody okay? So let's think about some of the parts that we're going to need for this. We're going to need to evaluate the vector field at every point on the surface. So somehow we're going to have to describe this surface to this f dot dA through the integral. Somehow we're going to have to include all the points on the surface to get at this dot product, to plug into the dot product f dot dA. We got some sense of what f dot dA can represent. It's how much of the vector field is flowing through the surface. Think about where we saw vector the flux integrals before. Let's actually not. Let's think about where we saw flux integrals. Not going to pick. So here's the divergence theorem. The integral over some solid W of the divergence of f times dv. Regular old multiplication, divergence of f is a scalar. Remind ourselves of that. The divergence of f is a scalar. So this is regular multiplication. Not a dot product. W is a solid. And S is the surface of the solid W. Remember, we're thinking of these surface integrals, these flux integrals, as the vector field flowing through the surface. So let's put this stuff together. So we're calculating the divergence times dv. So at every little chunk of the solid W, we're going to assume that the divergence of the vector field is constant so that we can multiply. Same thinking that we always apply in an integral. We make things constant or over some small piece. So dv is some chunk of we've got the same kind of parts. We got some small chunk, the solid W. We'll multiply that volume, it's a volume, so it's some volume. We'll multiply by that divergence of the vector field, whatever that might be. And we'll do this at all the points in the solid W and add them up. The fundamental theorem of calculus, the divergence theorem, says this integral dv is the same as the surface integral over s of f dot dA. The surface integral is measuring how the vector field flows through the surface of the solid. So the surface integral remember that the surface integral is measuring the flow of the vector field through the surface S. So what the fundamental theorem of calculus is saying in the divergence theorem is that we can calculate the divergence at all the points in the solid by calculating how the vector field flows through its surface. All this stuff going on inside the solid can be calculated by looking at the vector field flowing through the surface. Question? We still don't know what divergence is. It's some kind of thing that we do to a vector field that comes up with a scalar. Not sure what it is yet. We know from its position in something that we want to call the fundamental theorem of calculus, the divergence theorem portion of the fundamental theorem of calculus, that it has some kind of, it acts as some kind of derivative. But we can calculate the divergence at all the points inside a solid by looking at how the vector field is flowing through the surface. It evaluates on the interior by adding something, the antiderivative at the boundary. We're evaluating on the interior. We're adding a bunch of stuff inside the solid by looking just at what's going on at the boundary of the solid. That's what the fundamental theorems of calculus do. They tell you what's going on in the interior by looking at what's going on at the boundary. As long as we have that particular relationship between the two things that we're adding. The antiderivative, for the case of the fundamental theorem of calculus. The potential function of some gradient field for the fundamental theorem of calculus for line integrals. The vector field, where we're calculating the divergence of that vector field. The same kind of structure. Evaluate at the interior by looking at some kind of antiderivative at the boundary. We also had a flux integral in Stokes' theorem. where we want to look at the flux integral of the curl of a vector field at every point on the surface. And we can analyze this by calculating a line integral of the vector field just at the boundary of the surface. So we should note that curl of F is a vector. And so this is not regular multiplication, this is a dot product. dA is still some small piece of the surface S. And it is normal to the surface. S is a two-dimensional surface. And C is a one-dimensional boundary. That's the one-dimensional boundary of the surface S. So the line integral around the boundary of the surface S of the vector field is telling us about how the curl of the vector field is flowing through the surface. Questions? Of course, no questions, because what I've just said is just way too vague to be able to form a question right now. From a student standpoint, we're like, oh, how is this going to show up on the final exam? What am I going to have to imitate on the final exam to successfully complete this task? Don't worry about that now. That's for later. The things that we want to think about. How integration works. The base assumption. Assume that the continuously variable part is constant for some small piece of whatever the set over which you are integrating. Be that set an interval, a curve, a surface, or a solid. Be aware of what we can model our integrals with, the important integrals that show up, line integrals and surface integrals. They're based on multiplication. Multiplication with one of the factors is continuously variable. In vector calculus, that multiplication can take the form of a dot product. So we got to think about what the dot product represents. We have to go into all these extra details that we didn't have to do in single variable calculus, because in single variable calculus, everything was just multiplication. And so we were able to get applications of integration by just looking at applications of multiplication. But now that we're playing with vectors, our multiplication is dot product. We've been using dot product. Dot products and cross products, focusing on dot products. So now we've got to look for applications of the dot product to tell us about applications of line integrals and surface integrals, or flux integrals. Questions? Comments? Mind remark? All right, so as you know, next week is spring break. So a bunch of assignments are going to show up because I don't know about you. If you're going to be planning on catching up during spring break, I recommend that you just make a break, take a break, worry about when you come back. Don't forget anything, but worry about when you come back. Take an actual vacation. But as an American that grew up in the 80s, I can't just take a break. I'm probably going to be using that break to catch up on some work. So if assignments show up, you feel free to ignore them until you get back. I won't have any due date. If I set a due date for Monday coming out of spring break, that's because I missed what day it was. And the due date will be a week after coming out of spring break, the second week of April. I'm going to try to pace out the rest of the assignments for you to work on. All right. The other reason I'm going into wrap up voice is I'm not able to hold a meeting tomorrow, Friday, at noon o'clock. So no meeting tomorrow. That's going to do it for today. That's going to do it for this week. Everybody have a good spring break, and I'll see you on the Monday after next. Thanks for playing.